I mean, those are the places where they show the highest sensitivity to the value of the heavy quark mass. So as a matter of principle, this is the ideal place. You may have theoretical problems, but from the experimental point of view, this is where you have the highest sensitivity. So, okay, so we have the two concepts, heavy quark mass, heavy quarkonium. Let me elaborate a little bit on each of them. For the heavy quark mass, we have infinitely many definitions, but there are some that we use more than others. One is the mesh-bar mass, which is actually a short-distance mass, which is the mass that appears naturally when you consider observables at high energies, actually above away threshold. The other definition that appears naturally is the Ball mass, and this appears when you consider heavy quark physics near threshold. So actually, the one that I will discuss in this talk are determinations of this quantity. Not really of this quantity, but something related to that. So what do I mean? So I've stated what I'm really going to measure, so the Ball mass. I will elaborate even further on this later. What are the observables that I will consider? Heavy quarkonium. For me, heavy quarkonium are going to be systems such that the quark is heavy enough and that you are near to threshold enough such that you can do perturbation theory and you need to do a Coulomb resummation to describe physics properly. So indeed, this is a non-perturbative scenario. You have to resum an infinite number of diagrams, but it is still weak coupling. So this heavy quarkonium is non-perturbative, but can be computed using weak coupling techniques. So these, places where this Coulomb resummation is necessary. Okay, well, maybe before going into that, let me elaborate a little bit more on what do I mean by this Coulomb resummation. The point is that when you have the heavy quarkonium, a QQ bar system, the velocity of the heavy quark is much smaller than 1. The fact that this is small is the near threshold idea. And then you have this hierarchy of a scale, the heavy quark mass. This I will call it soft scale. This I will call it ultra soft scale. So you can multiply the heavy quark mass by this small dimensionless parameter velocity that makes each scale to be smaller than the other. This is a natural place to use effective field theory. And then we face the situation where we have alpha divided by the velocity, which is of order 1, and then all terms that, for instance, we have here contribute equally to the observable. Actually, this calls for a Schrödinger equation, and an effective field theory formulation to this problem may come by the use of the effective field theory named potential NRQCD. And then what we try is to resum systematically these effects. This will be the leading order. If you multiply this, obviously the coefficients will be different by alpha and b. This will be next to leading order. Next to leading order will be alpha squared, b squared, alpha b, and so on. Similarly, you can as well try to resum logarithms. So besides having, you need to resum this because of the Coulomb resummation, and on top of that, you may parametrically consider that alpha times log is of order 1 and perform this resummation. So this is what one can try to do. And okay, where are places where this should be done? Heavy quarkonium masses. And actually, this is going to be the main topic of this talk. Non-relativistic sum rules. Unlike those that we have seen in the previous talk, which are for low n, if you take n, the number of the moment large, then you have to do this resummation. And another place is TT bar production near threshold. These two places are ideal in principle to get in the determinations of the bottom and or charm mass. TT bar production is a good place if we ever get the linear collider to get a determination of the top mass. This I will not discuss in this talk because I'm really going to have time. So I'm really going to focus into these two, and actually within these two, I will focus more on determinations coming from the heavy quarkonium mass and see what we can get. So those that I will discuss are those in blue. Those are determination of the bottom mass, either using a spectroscopy or some rules. In black, I will not discuss. They are also coming, if you want, from heavy quarkonium. But for low moments, but still on the experimental moments, they use the experimental values of the masses and the decays, maybe except for the lattice, that they use directly lattice simulation. This would be for the blue are the ones that I'm going to discuss for bottom, and these are the ones that I'm going to discuss for charm. And again, there are also these other determinations that I don't discuss. They had already, well, either in the previous talk or in future talks, they will be discussed in more detail. So not here now, unless there are questions. No, so now let me go to these determinations. I start with a spectroscopy. And actually, it's nice because theoretically it's very clean. Basically, the whole theory can be summarized into this formula. I mean, you have the spectrum, the heavy quarkonium mass, with some quantum numbers, principal quantum number n, l, whatsoever. And then you have twice the mass. This will be for BB bar or CC bar, or bottom charm, there will be masses different. Then you will have as well here the reduced mass. And then you have alpha squared, alpha cubed, alpha to the fourth, and alpha to the fifth. This is what is known at present. These P1, P2, P3 are logarithms of the scale nu, and actually at this order, some extra logarithms appear because at this order, the fact that you have what I call it the hard scale and the ultra soft scale show up here. And actually, this produces this log here, m alpha to the fifth log of 1 alpha. So this first appear here, and here you see different an historical overview of the alpha to the fifth contribution here. Actually, this wouldn't be even fair, because this is only the computation of the spectrum. But to get this, there are some intermediate computations that had to be done first, which are in particular the potential, which are difficult building blocks in order to reach this accuracy. So what we are going to use basically is to get this from experiment and to fit it to this. And we will do to N3LO. So as simple as that. Actually, experimental error, 0 in our case. We will have other problems, but experimental is not one of them. We may consider the summation of logarithms. I mean, not as I explained before, in the sense of considering alpha log to any power. But the ideal thing will be to have the N3LL for S-wave states, and this is not yet available. At present, this accuracy is known for hyperfine and P-wave. But to really, the ideal place to use this result for the heavy quark mass will be S-wave ground state, and this is not yet complete, but eventually in the future. So I will focus only on determinations from here. So this is part of the problem. So now we have this, and I didn't specify, but all this was written in our reference mass, which is the pole mass. But this we cannot really use. And in particular, we cannot really use if we want to determine the MS bar, which is our reference value with which we compare all. And the problem is that the pole mass has this perturbative expansion in powers of alpha, and we have these coefficients Rn, and renormalons, if we believe them, predict that they have an n factorial. These coefficients have an n factorial behavior. So actually it means that this series is divergent. We cannot assign a number to this sum. It's not a number in the real axis. So basically what it means is that we have MS bar, we have powers of alpha, alpha is small, so this will be smaller than this will be smaller than this, etc., because of the powers of alpha, but at some point, the growth of the n factorial overcomes the suppression of alpha, and the series starts to diverge. If you truncate the series at the minimal term, you get an ambiguity for the Lambda-QCD. So this is the problem. So we cannot work with the pole mass. Let me elaborate on this in the Borel plane. If you can actually study this in more detail, the structure of the renormalon in the Borel plane, I mean, if you do the Borel transform, which is this will be the inverse Borel transform, in case you could do it. And then the first singularity is what dictates this n factorial behavior. And actually, this can be determined only using renormal operator proto-expansion, consistency. All this, I mean, where it is and the structure of the singularities, the only thing you cannot determine is the normalization. It could be 0 if there is no renormalon. But this normalization actually can be determined if we take, for large n, this coefficient should be dominated by this behavior. And this we can check. Actually, we could use the pole mass or the static potential, because this combination is renormalon free, and then determine the normalization, NV, which is NM, using the ratio of the asymptotic expression. The asymptotic expression is this, except for a factor 2, and versus the exact result. Notice that this is logarithm. So we have logarithms versus linear behavior. At the lowest order, the linear behavior is this. So we have no logarithm and the linear behavior in nu. But as we increase n, things get flatter, and this is a value that one obtains using the static potential. Notice that this determination of the normalization, in principle, uses zero information on perturbation theory of the pole mass. So we can determine this number approximately, so we have an approximate knowledge of the normalization of the renormalon. And this we will need later, though I have to say that this error plays a minor role for what is the real uncertainties that we will have in the problem. But we need a number for this. Actually, if the determination is sensitive to that, it means in an indirect way that you are sensitive to higher order perturbation theory. So, okay, so we have a theoretical expression of this. In terms of the pole mass, we have a more or less a knowledge of the renormalon structure of the pole mass, and then what happens is that this is an observable, so it's renormalon free. So and actually renormalons appear because we do the factorization between different scales when we treat the problem theoretically. So we have a renormalon here, we have a renormalon here, but they canceled in the combination. So this expansion has also a renormalon, which is the same up to factor -2 that we have here. So a way to deal with that is to subtract it. This can be done in several ways. And I show one. Is that we have the pole mass, we subtract really the renormalon, which has this structure, we re-expand in powers of alpha, and then these coefficients, they don't have an n factorial anymore. They are of natural size. So basically what we do is we subtract and add the same contribution here. So when we look at the same object down here below, this object doesn't have renormalon, there is no n factorial here, and this object, which is this perturbative expansion, does not have renormalon either. This I've shown what is in the scheme, what is called the renormalon subtracted scheme. Renormalon subtracted scheme will be with 0. Renormalon subtracted scheme prime will be with 1. In principle, the renormalon shows up at higher n, so starting at 0 or 1 shouldn't make a difference. So you may use it as a test of the dependence of the computation to how you implement the renormalons. You can use as well other schemes to subtract the renormalons that I quote here. What they should happen with them is that in the asymptotic, they should have this behavior. They have the renormalon. What they will be different if one is at low orders, but they should converge. And you have the PS, the M as R, the MRS principal value. These two are kind of different from this, but this I will not discuss in this talk. So now we have everything. We have this from experiment, and we have this theoretical quantity. And what we want to determine is this, and once we have this, we can obtain the Mesbar mass. So this is the procedure, how far we can get. And we have not up to infinity, we have up to 3. No, yes, alpha squared up to alpha to the 5th. So, okay, so what is the issues? What is the experimental data that we are going to use? We have the spectroscopy from BB bar, CC bar, and actually also from relatively recently from B sub C. Options, what is the data set? We could take only the ground state. We could take ground state plus excitation. We could take only pseudoscalar vector. I will make some discussion about this. What are the differences we may get? In the case of the bottom mass, we may also have effect of finite mass charm quark effects that I will discuss. And I will also discuss, which I think is the major issue here, about ultrasoft effects and his relation with non-perturbative effects. I mean, this is really the major problem. In the case of the bottom, as I said, the issue, and one thing that I advocate strongly, is that actually you should work with 3 flavors. I mean, in principle, you have the soft scale, and this I would say was not seen early. Effectively, it's better the mass of the charm is larger effectively than the soft scale. Obviously, here there are numerical factors. What maybe it was not that common, typically, including myself, in the past I was using 4 flavors in the relation between the pole mass and ms bar mass for the case of the bottom. What happens, because you will say, okay, the bottom mass is larger than the charm mass. So the natural thing is that in this relation between the pole mass and the ms bar mass will be to do the perturbative expansion with 4 active flavors. Instead, but then one realize that actually what you consider loops, n is the loop, what you have effectively is that this scale is smaller than this. So when working with 4 active quarks, assuming the charm to be massless, you get corrections which are order 20 MeV with no convergence. When you rearrange the perturbative expansion, you get very tiny corrections which are actually of order -2 MeV. So when we do determinations with the bottom, we will work with 3 flavors, always. And then this will be a tiny correction. And actually, this has also, in later papers, been confirmed to higher orders. Okay, so I take one observable for illustration, and the observable that I take is the mass of the eta V. So I want to determine this. Actually, the uncertainty is the yellow band. And this is in the RS scheme. If you remember, was one of the schemes that I defined before. So this is twice the mass. This is the alpha square, alpha cube, alpha to the 4th, and the black line is alpha to the 5th. And this dotted is alpha to the 5th subtracting the ultrasoft. It's a way to estimate uncertainties. So you see convergence, but if you want, the magnitude of each correction is large. What typically happens is that if you want to consider the RS prime, I mean, if you introduce the cancellation of the normal on at higher orders, you accelerate the convergence. So and notice that this is assumed compared with this. So this is an order of magnitude better. Well, no, I don't know. I mean that this is 100 MeV scale, and this is 50 MeV scale. So now here you have twice the mass. I have to remember alpha square, I have to remember, yeah. Alpha square, alpha cube, the green is alpha to the 4th, and the black is alpha to the 5th. So this is, again, all of them lay more or less on the same ballpark. One thing to say is that both determinations are virtually identical, which is good. Pointing out that the way you implement renormal subtraction is not an issue. And here I could make a long discussion about errors, but to the point. What is the main source of the error here? The main source of the error here, in the way we estimated it, is the new dependence. To make it clear, if we take nu 5, which is what we did, the error estimate is from here to here, which is basically this. If you duplicate, so basically it's 30-something out of 37. You have other sources, in particular the normalization, but it's really if you consider this scale variation. As an aside, ultrasoft effects appear not to be important, but on the other hand, if you compare this alpha to the 5th, compared with the green, yes, the green is, yeah. You compare with the green, you see that the scale dependent is bigger. This could be due that at order alpha to the 5th, there are new scales, I mean the hard and the ultrasoft. So maybe here resummation of logarithms could be important. Now let me go to the other issue, is that about the error or points of worry. I mean here, rather than hiding the problems, I'm overemphasizing them. And one problem that could show up is this, ultrasoft effects show up. So you have kind of the perturbative part, I call it soft, but actually there are also hard corrections here. This you believe that you can do perturbation theory, and then you have something that appears at ultrasoft scale. I remind you, ultrasoft scale is m alpha squared, up to numerical coefficients. You can write it in a compact way in this way. This is purely perturbative and actually quantum mechanics, and this is a correlator. And this object you can compute in perturbation or not, depending on the relative size between lambda QCD and m alpha squared. If you assume this, then you can compute this in perturbation theory, and we get the N3LO accuracy that we are using, and then the leading corrections are non-perturbative leading corrections are local condensates, which actually they are known to order 4, 6, and 8, but we don't use them. One reason not to do that is because I don't really know what are the values of these condensates. This has very large uncertainties, but most of all, from my point of view, is that before using them, we should see the onset of perturbation theory associated to these condensates. I mean, if you have a condensate, perturbation theory should be divergent, and you should see that. And in principle, we don't see that. So it will be premature to implement them. And it will be premature. Eventually, maybe, but we have to, let's say, we have to understand perturbation theory better before making a dedicated discussion about local condensates. If we instead consider that lambda QCD is bigger than m alpha squared, this will be the scaling, the leading non-perturbative contribution. Basically, what you have is that you expand the exponential to 1, you get the value, expectation value of r squared, which is this, and the integral over t of this object, which is non-local, scale like lambda QCD cube. So this, we don't really know a priori what is the situation. Okay, so then we have this spectroscopy determinations. There are different. The one that I've shown is this one, which is using ground state pseudoscalar. This one is using the vector. This one is using average. And one is using average and also including higher excitations in a global fit. Let me make some few comments, because from here, okay, first observation, all of them are consistent with errors. Actually, the way renormalon has been implemented in them is different. So this also says that renormalons, how you implement renormalon is not an issue. But I see a trend. So let me at least say a few things, because if I compare this with this is pseudoscalar, this is vector, and this is something that we will see as well for charmonium. And this systematically vector gives larger than this. And so this is in the middle because it's an average. And actually here, there is, so this could be due because this difference is associated to the hyperfine, and the hyperfine with this level of precision is not well described by perturbation theory. I emphasize with this level of precision, with fixed order. Resummation of logarithms here helps, but has not been implemented. So this we see. So this is, okay, maybe I shift now to charmonium, because otherwise I will. So now for the determination of the charm mass, in principle now we have two ways to determine the charm mass. Either directly from the eta C mass, which are these two. Again, one is RS prime, or considering this difference. I mean, this is the BC mass, bottom mass plus charm mass in a first approximation. And if you subtract the mass of the eta B divided by 2, you eliminate most of the bottom dependence, and you get an alternative determination of the charm mass. So you have two ways. Again, this is RS convergent, but large correction, RS prime, you converge to what you expect to be the right result quite quickly for the eta C. This is for the BC minus eta B divided by 2, a similar trend. Just for illustration, you don't need to see all this. Here, actually, you have errors from different sources, though nu is still dominant. But let me just to illustrate the point, because I think it's nice, because these are two different determinations from completely different source. I mean, this is RS, RS prime. These numbers are different, as they should be. But when you transform them back to the MS bar, you get them equal with 5 MeV difference. Similarly, for the BC minus eta C divided by 2, this different from this. When you consider MS bar, they are equal with 7 MeV. And if you compare this number with this, within 5 MeV, they are equal, with completely experimental setup. And this is a number. And this is good for one of the worries, because you may worry that non-perturbative effects are important. If they are, in principle, you would expect different determinations using both systems, because this will be in general. But I mean, if I assume that lambda QCD is bigger than M alpha square, this will be the scaling of the leading non-perturbative correction. In one case, notice that those are expectation values of R square of BC eta V, and this will be for the eta C. So if you get the same number, it means that this is minus this. It could happen. Numerical accidents happen. But if not, let's say either this is small or there is a numerical accident in the cancellation. So this, again, these are the determinations that I've shown. Actually, in our case, we took the pseudoscalar from this because we thought that the BC is more perturbative. I mean, we use BC and eta V at the end. It's more perturbative than the charmonium, but everything is perfectly consistent. This is from the BC minus eta V divided by 2. This is average of jet psi divided, an average of jet psi and eta C. And this is a determination of a global fit of charmonium data. So within errors, all three are consistent. So maybe extra comments. So I said something already. Vector fits appear to give larger values. Possible explanation in perfect splitting sensitive to resummation of logarithms. Actually, resummation of logarithms will increase sensitivity to smaller scales. Experimental precision is infinite. So actually, I should say, excitations are not needed. Not necessarily will lead to a more precise determination. On the other hand, they could be good. I mean, this will not give problems if theoretical errors are properly introduced, but they could be good because they could validate the method, in the sense that if we really believe that non-perturbative effects are small and we see not a big crash in the next excitation, this is a good signal. So, okay, this is what I wanted to say about heavy quarkonium mass. 5 minutes, okay. And then I will rush to the non-relativistic Sun rules. Here, again, there has been an enormous effort in getting them to N3LO precision. In particular, you have the current, electromagnetic current, that you do the non-relativistic reduction. You have the Wilson coefficient, V1, which is now known to N3LO, to this precision. In fixed order, you may as well consider resummation of logarithm. It's known with next to leading log. For the ratio, also with next to leading log. But B1, which is for the vector, and B0, which will be for the pseudoscalar, they are not known with complete next to leading log. But there are some partial computations. So the situation, this is the situation about the Wilson coefficient. For the vacuum polarization, schematically what you have is this Wilson coefficient square. Actually, there are some leading. And this non-relativistic Green function. This is the spectral decomposition. This is the discrete part of the spectrum. And this is the continuum. So this is the situation. And with that, in principle, you can compute a variety of observables, like decays of the heavy quarkonium into E plus and minus, also to pseudoscalar with B0, TT bar production. There will be some talks in this conference. And the ones that we are interested in is the moments, non-relativistic moments. And here, my point is that for large N, the contribution from the continuum, which could be one of the worries for low determination of the heavy quark mass from low momentums, is suppressed. And actually, for us, it's not going to be an issue. We have others, but this not. And then this is from the theory side, and this can be computed from theory, and this we also have. So we equate this to this. This is an old, but just to show the point, I mean, this is a partial computation with NNLL. This is the leading order. This is next to leading order, and this is next to leading log. All this is complete. This is next to leading order. And this is NNLL. So the resummation, and this is in the PS scheme, and this is in the RS scheme. The resummation of logarithms here seem to play a role to make things flatter. And actually, you get this number. This is a relatively old number, and as I told you, they show little, basically zero sensitivity to the high energy behavior of RBB. Whereas back then, when we did the analysis for N6 or smaller, we get errors associated to experiment of order of 50 MeV. I understand that situation has improved since, but still not sure that much, how far the experimental error has shrunk. Now, this is the situation, the one that I've explained. There has been ongoing computation since, but I didn't find a plot in terms of news, so I didn't show, by Andreu and Max Stelhofen, where they include extra corrections, ultrasoft extra corrections, next to leading log, still incomplete. So here there are extra corrections, ultrasoft, that are not included here. On the other hand, here, the correction associated to the spin-dependent Wilson coefficient, which is known, and is scheme-independent, is not included here, but is included here. Either way, they are both consistent, and typically they have larger errors than these other determinations. I mean, there are some work to be done here before being more competitive. And now let me, okay, and this has also been done for Charmonium by Adrian. Let me go now to the final sum rules. Also in a tremendous tour of force, the sum rules have been obtained for large N to N3 LO precision. For reasons that I don't understand, the leading order is not plotted here for the 10th moment, which it will be good for you. I mean, it will be, and that's the reason you also see here. It will be from 4 to 3. Yes, this is PS. From 4 to 3. So it will be from here. So this will be the leading order, next to leading order, next to leading order, and 3LO. So looks nice in principle. Though I have to say that here, to make this convergence, you have to do the analysis with relatively large mu. Compared here, these plots were done with a smaller mu scale. This is what we would expect a resummation of logarithms would be good at. So this is good. The authors, they have still this worry about the continuum contribution. In principle, you would expect that when you increase the velocity, the perturbative, the continuum contribution should converge with fixed order perturbation theory, but they don't. To show the point, is we are talking about this correction here. So it's something that should be investigated, but to be honest, I'm not sure we should really worry about this about splitting contributions too much. And also it's a tiny contribution to the total number. So this is what they get, and this is the number that they compute, which is this one, which is N3LO. Just for completeness, I also mentioned this one, which is also N3LO, but not complete. In particular, the continuum contribution was not included, and actually there was an aggressive statement about the errors of higher order perturbation theory. And the difference, and this actually is something that maybe we can discuss, the difference between central value has to do with the implementation or whether charm corrections are large or not here, which is something that should be understood better for the case of non-relativistic sum rules. Okay, with that I finish. Yeah, and I go to the conclusions. As a matter of principle, heavy quarkonium near threshold observables are ideal. If not, it's because of theory, not because of experiment. They show higher sensitivity to the heavy quark mass. They are clean. Theoretically they are clean. Differences, and even they have different systematic than alternative determinations, and we get similar numbers than alternative determinations, which is good from the point of view of worries about non-perturbative effects. For the spectrum, something that we should worry is that from NN-LO to N3-LO, there is an increase of the scale dependence that should be investigated, which could be related with these possible issues on which we would like to get a better understanding. The ultrasoft scale versus lambda QCD, as I told you, new effects show up at N3-LO. Perturbative ultrasoft effects appear to be small, at least with fixed order computation, but renormalization group improvement will clarify this further. We don't see the existence of order lambda QCD square effects. Actually, this is as well supported to some extent by lattice simulation of the static potential, which I think we will see in some talks in this conference. Still, I think a lattice simulation of the ultrasoft correction, that the formula that I've shown before, is a must to really make the heavy quarkonium mass determinations of the bottom mass competitive. Maybe a final observation, non-perturbative effects. I'm not worried if perturbation theory is convergent. I don't worry about non-perturbative effects, but as a matter of principle, they are equal parametrically in some non-relativistic instrument rules than in heavy quarkonium, though the overall coefficient is significantly smaller in some rules, something that should be understood and quantified. And just to trigger a discussion, maybe a merge between relativistic and non-relativistic instrument rules, when use one versus the other, for which value of n this should be clarified, or if there is a region where both could be applied, and for the case of relativistic instrument rules, to what is really the dependence with the continuum. And that's it. Thank you very much.
Questions?
On the non-relativistic sum rules, you can see that the coefficients that multiply these condensates, they're growing strongly with n, like some power, like I think the third power in the gluon condensate, and I think it gets worse for our higher condensates. Shouldn't that really limit the application of larger n?
Well, for the authors should, but let me say, okay, this has been done with n equal 10, which is relatively conservative to me. And you should, I don't know what is the value of the gluon condensate. Will be my first statement. The second statement is that I would not worried about non-perturbative corrections until I see that the perturbative expansion, the series, is divergent, and that it scales as expected because of the next order in the operator Proth expansion. I would, as I say, there is, well, the theoretical formula is known. But I think that error parametrically is smaller than higher order corrections in perturbation theory.
From the gluon condensate?
For some rules, for non-relativistic.
But what about higher condensate?
What I mean, let me repeat that. What I mean is that this M10 is known to N3-LO. What I mean is that it will have a higher impact to compute to a higher order than considering non-perturbative condensates. Parametrically, non-perturbative condensates are smaller. They are exponentially suppressed. So until I don't see this exponential behavior in perturbation theory, I don't see the point of introducing them.
No, but the coefficients grow. That we
know.
The
coefficient grow, yeah. But it's a coefficient that grows times a constant that you don't know. But this coefficient growth, you should see also in perturbation theory. Actually, this is something that I would like to do. This has been done with n, what should happen, what you say, you should see also in perturbation theory. And this is an exercise that I would like to see. That if you increase n and n, at some point perturbation theory should break down. I don't see an analysis, increasing n arbitrarily and see that perturbation theory breaks down. And it wouldn't be that difficult to do, indeed.
Okay. Since you mentioned charm quark effects, maybe I can comment on that. I think conceptually it's not a big problem. It's rather that there are two calculations and they don't agree. And of course, we think that our calculation is correct and charm quark effects are small. And this is, from my point of view, this would also be another indication that also non-perturbative effects are small because, well, generally corrections from small energy scales would be.
Okay, on this I have a question. Because, here versus here, if I understand correctly, what they use is an estimate from a paper of André Oang, but they have the formulas. André has a formulas, whereas in your paper, are there formulas? There are an explicit computation of the charm corrections? Because in principle, you can compare formulas and see whether you agree or disagree.
Yes. So I guess I would have to look at this again, but we weren't able to do an exact calculation with exact comparison with what was in André's paper. So from the expressions we had, it seemed that everything would agree, but
you mean that at some point in the numerical implementation?
At some point.
Okay, but this should be clarified. Yeah, I would say.
We would love for someone to clarify this.
Okay.
We think that what we've done is correct.
Okay.
I have a question regarding the nomenclature about large and small ensemble when it comes to lattice QCD. So some of your slides you refer to JL QCD results as using large ensembles, but I would think it should be small because they never went to very high moments.
You mean this one?
Yes. Well, no, that's HPQCD in the previous slide somewhere. The JL QCD.
You mean for harmonium?
Okay.
Yeah.
Right. So why? What is large and what is small?
Yes, I don't know why we put them here. Maybe it should be moved here. And actually, to be honest, this is here because of historical reasons. But the original idea was only to put heavy quarkonium, that needed near threshold, and at most to put determination of low-end sum rules that use experimental data, which are some of these. Actually, others use lattice for the moment sum rules, and in particular this one. But yes, I agree, this should be moved. Should be moved here because 6, 8, 10 could be considered here. Mm-hmm.
So do you think it's feasible, theoretically, to do non-relativistic harmonium sum rules, or just too low scale?
On this, I would do it. Moreover, the formulas are there. There is even a program to implement that. We have 3 terms. In principle, you would say mass of the charm is 1.5. So you would say it's pretty low. But all this is multiplied by coefficients. You have ratios. You can do parametric resummation of effects. And perturbation theory will tell you, whether the series is divergent or not. Well, if you find that the next relation is higher than the previous and the other is larger than the previous, you say, okay, obviously this is nonsense.
But from my experience, we tried relativistic sum rules with n equals 2, and we already found issues there.
For that issues of convergence.
Yes, and lack of solutions.
But this is what I'm saying. Then you will see them as well in non-relativistic sum rules.
Further questions?
Also, let's say, I mean, your computation should tell you that you are doing it wrong. If not,
Indeed.
you have a problem with your computation. The computation should tell you that you should not do this. You should not use this formalism in one place because the thing doesn't converge at all.
I don't see any more hands, so perhaps you can thank Antonio again. Now we have Pere Masjoan, also from Barcelona, talking about quarkonium.